Okay, good morning. Let's begin. So, we are in the week two of this CS217 machine learning. This week, you will have your lab also on Thursday from 2 to 5, where you have been instructed to implement the star algorithm and then run it on the 8,000 problem. So, for this, it is necessary that we understand the star algorithm thoroughly. Is worth spending time on instead because it is one of the pillars of AI. My goal is that before itself, all the important milestones of AI should be covered, which are classically mentioned. So first is A-star, then the perceptron and perceptron training algorithm, then predicate calculus and resolution application. These important milestones should be covered for the midterm. Now, main points covered last week in the week of 6 Jan 2025 are the following. Course website is very important. You have been told to visit the website. Always the slides are going there. And also the pointer to the recordings of lectures will be there. Topics, references, everything is well laid out in that website, including PDF of the books, textbooks, which will be covered here. For A-star, I'm mainly using Niels J. Nielsen, the second book in the reference list. Niels J. Nielsen for A-star algorithms. Now, we also covered the AI areas, search, reasoning, memory, other areas, little bit of planning, which is what we want to cover until mid-sem. And then after mid-sem, we go into applications of AI, which makes the field so interesting and impactful. Like the same vision, expert system, robotics, and so on. Then we covered Turing test, where an interrogator is asked to distinguish between a human being and a machine. And if the interrogator fails to do so, then the machine is said to be successful as an AI agent. And the distinguishability is not only for communication but also for action. If a robot's actions cannot be distinguished from a human action, then again the robot is passing the Turing test. So this was contested by Saad, a philosopher, who proposed this challenge of experiment. A person is interacting with a Chinese speaker outside the room, and the person is simply mimicking a set of rules, which is all covering and universal with respect to Chinese communication. And the communication is such that the outside person, the Chinese native speaker, cannot cannot understand if the person knows Chinese or not. Okay. So the human being gives an impression of knowing Chinese just following a set of mechanical rules. So the person inside the room himself says that I do not know anything. Okay. Then how come this impression is created? So that's why indistinguishability, as told by Turing, is said to be not sufficient for intelligent behavior. So this is a challenge to Turing test. Then I also mentioned the guiding scheme, Mixel 30% and Cell 50%. And there are two quizzes, 20% each. CS 214, the weekly lab will have 10% weightage, and the mixum exam 10%. Final Viva will have 20% weightage. Okay, so we also started the general graph search algorithm, and the most important point about this graph search algorithm is the introduction of two data structures: open list and closed list. Okay? And open list maintains the list of nodes which have to be expanded. That means those children need to be brought in. And closed lists are those who have been expanded, which have been expanded, and the children have been installed in the open list. Okay? So this is the basic idea of algorithm supported by this data structure. Open list and closed list happen to be the most important component of the algorithm. Now, the The search can become intelligent if we pick the correct route, okay, and not on the optimal path all the time. Because the goal of the install algorithm is to find out the optimal path. So in the lab, when you do the assignment, your task will be to solve the optimal path, starting from a configuration of the person to the destination configuration. Okay? And there is also unreachability there. Not all configurations reach the given destination. Okay, so if you have the destination 1, 2, 3, 4, 5, 6, 7, 8, you cannot reach this destination from all other configurations. And this can be proved. So what will happen is that the open list will become empty as the destination state has not been reached. Okay, this is how the algorithm will behave. Now, this algorithm is required to be efficient. That means to not expand useless nodes. Okay. So what is the condition for that? So that the optimal path is reached, and also as few uh, useless nodes as are expanded. Okay, that is the main idea. So open list, closed list, you have to understand very carefully, and you also implement it in your assignment in the class. The log search algorithm has been described in these steps. The most important step is step number 7. Establish a pointer to send from those members of M that were not already in J. That is, N has been expanded, okay, and no, through an expansion, N has trapped in open list, and is to understand this algorithm step by step, which will happen only when you implement. Okay. Then, these are the main points that are displayed. And let's go to extra. Again, and I have to some foundation report regarding human brain, human psychology, and so on. So, as we know, the state space is the most important point about any kind of search algorithm. You have to go from state to state and start from the start state. You have to apply the operators. The goal state is one of the destination states, and cost is the effort involved in using an operator. The operator cost is the least cost. For this problem, the 8% problem, this is the starting state, and the destination state is this, which has to be reached. Here, the state is very simple. It is this matrix itself, along with the black space, which gives you the state. But for a problem like chess, the state is going to be the state space is going to be much more complex. Right? But in spite of that, you know that AI agents routinely beat human beings, except for some extremely gifted ones. And, chess is a losing game for human beings because of the sheer computing power. The AI agent can navigate through the search space in an enormous number of possibilities. Okay. And it navigates it in no time, so the response time is also extremely quick. And human beings cannot, by brute force, see so many states. Then the intriguing question is, why do human beings, and after all, win some of the games? Okay, what is the intriguing thing which human beings employ to win against the computer purchase? Okay. So this is something which we need to think about. And human beings also have at their disposal an extremely large number of previously played games. Okay, so if you, for example, see recently interviews of Kasparov, Karpov, Bobby Fischer, Anand Vishwanathan, and so on, these players go through a very, very large number of already played games. Okay, and maintain that history in their mind as to what was done in particular game. Okay, so in that sense, human beings are also going through a learning process, some of which is storage of configurations in the mind. So this is the computer does by brute force and in a very speedy manner, visiting all the states. So this 8 puzzle problem is far simpler compared to what you see in chess. And in chess, again, chess is really far simpler compared to everything that we do in real life. When we understand each other's communication, we look at a scene and understand is this scene a dangerous situation or not? Should I save myself or not? If there is some disease in the body based on symptoms, these are far more complex. In fact, things which are very easy for human are extremely difficult for people, which there is duration. Mathematics is one of the hallmarks of human activity, extremely complex, very sophisticated. But computers have made inroads into mathematics. But computers are nowhere near children intelligence or intelligence of playing a role in terms of pattern recognition. We'll make some remarks about machine intelligence and human intelligence, the differences between them. Okay. So now general graph search is a very powerful general umbrella. So general graph search operates on open list of floor list. Out of the general graph search, one particular algorithm called A is our most important concern. Okay. So in general graph search, what happens is that in open list, the nodes are always sorted, okay, based on some scoring problem. So the general graph search algorithm becomes algorithm A. It's called algorithm A. If for every node in the open list, we associate a function f, which is g plus h. Okay. So g plus h is the following. G is the cost of the path in going from S to N. Okay. And h is the cost of the path going from N to a goal node. So it is a two-component function, quite intuitive and also easily understandable. That's known as S2. G always is maintaining the cost of that, which is least cost so far, which is least cost so far. Okay. And for H, there is no way of knowing the least cost path, otherwise this will not be a search algorithm. H is an estimate of the cost involved in going from a node to the node. Estimate. Okay. G is the actual cost of the least cost path at the current stage of the search process. Okay. So if this is the case, then you can see that the breadth first search, and A-star search are special cases of A. Let's see, equal to Gn plus Hn, where N is the node in the office. Node chosen for expansion is the one with the least. For breadth first search, H is equal to 0. Okay. And G is the number of edges in the path to S. G is the number of edges in path to S. If G is the actual cost, not the number of edges, but the cost of the edges have positive, non-negative cost. Okay, so edges have non-negative cost. Remember that. Then G is the accumulation of all the costs of the edges in the path. Then variance has changed. Right? What is the name of that algorithm? H is 0 and G is the actual cost in terms of the sum of the edge cost. It becomes a Dijkstra algorithm. Dijkstra. And D for DFS, H is equal to 0. And G is equal to 1 by number of edges in the path. That will give rise to the DFS algorithm. Right? So you see, these are the special cases. But for an AI course, the important is case that on which we will spend considerable amount of time. GL is the least cost path to any from S found so far. This is the one. HN now has additional restriction. HN is an estimate to the goal. Now, if HN is less than or equal to H star N, the actual cost. We are estimating the actual cost from below. Then this algorithm is called H star. H star comes from H star. So if the actual cost is H star and my estimate is HN, my strategy is optimistic. Okay, I have an optimistic behavior. I'm saying that the actual cost is less than the estimated cost is less than the actual cost. Therefore, time spent in reaching the goal is less. So this is called an optimistic strategy. And if H is less than or equal to H star, then we will prove this that optimal path is guaranteed. Okay. So you can remember H star algorithm by remembering this slogan. Optimism leads to optimism. Optimism leads to optimism. Now, another example which will help you remember is that throughout life. Okay. So this is my favorite example. Uh, maybe you have seen that Three Idiots movie. Three Idiots. Now, there, Mishman says that if you want to, uh, sort of have a positive attitude and reach your goal, achieve whatever you have to do, even if there are adversity and difficult situations, just say R is well. R is well. Okay. So remember R is well. So this H and less than or equal to H star strategy is called R is well strategy. Okay. Remember this as R is well strategy. That is the optimistic strategy. So the good thing is that this strategy leads to optimality. Then you might come back and say that make H and zero. Make it zero. Okay. Zero cost. I don't have to incur any cost. That is unrealistic. And what will be the harm if H n is zero? Yeah, but what is the harm? What is that? Yes. You will expand many nodes which are not on the optimal. Okay, this is something you will verify in the lab. Just apply breakfast strategy, apply the extra, and have an H star strategy, H star heuristics, access heuristics. See the way the number of nodes drastically reduce, the number of useless expansions drastically reduce. All of these will give you the optimal path. Benefits the extra HL which is less than extra. We'll see just now what are those units, what are the actual on the ground H stars. Um, uh, one of the H stars, one of the HNs which are guaranteed to be less than or equal to H star is display style setting. This I covered in the class last time. So count the number of tiles which are not in their correct position. You will need at least so many steps. Okay. So that will reduce the number of useless expansions compared to breakfast search or the extra. Verify that. The better heuristic is the Manhattan distance heuristic, where you take the sum of the x distance and y distance minus the power to get to its correct position. So if you take, for example, 3, is to move right one step and up one step, 1x plus 1y to 2. And similarly for each time, so this heuristic will expand even less number of units. This is also guaranteed to be the any heuristic which is less than h star will give you the outcome. It's guaranteed. Okay, so depending on which heuristic is closer to h star, okay, the actual cost, the heuristic is more efficient in terms of nodes. Okay. So let me pause at this point and see if any of you have any questions. Is it clear to you what is the you have to at least in the first class, you have to at least show the number of expansions for the BFS, uh, that stuff, and these two heuristics, manage heuristics and place right. Yeah. What is the meaning of long vision? Non-optimal. Never. Never. You just think about it. Okay. So, okay. So, yeah, but of course, there are expression non-negative. And if there's unreachability from one state to another, none of the heuristics will give the path. Local list will get it. And then it's kind of state in the extension state, you make it as 1, 2, 3, 4, 5, 6, 7, and choose various other states. Okay. You will also implement the visualizer variable problem as part of your assignment. Okay. So the critical points for each algorithm are the following questions, which might sound philosophical, but these are actual practical questions. Do we know the goal? Is the distance to the goal known? Is there a path known to the goal? These are all questions of life also, as you understand. And these are all very complex questions. Now, about the path, any, any time before H star terminates, there exists on the open list a node from the optimal path, all whose ancestors in the optimal are in the closed list. Okay, sounds very intuitive and commonsensical. If we go through the proof step by step, very slowly. I understand that the proofs are best done by writing on the board. Okay, but the advantage of going through the steps is that you can the proofs later for future reference. But let us go through the steps slowly. It's slowly. So this means there exists on the open list always a node n such that gn equal to g star. Okay, so there is a node for which you cannot better the path from start to end. Okay, so there is a node from the optimal path which is in complex, and all its ancestors in the optimal path are gone to the places. That means the optimal path to that node has been discovered. To that node. Okay, to that node has been discovered. There is always such a node. Let's see the proof. Okay, Luca. Let S N1, N2 up to Nk, N3 minus 1, Nk, where Nk is equal to G, B, and optimal path. Anytime during the search, there is a node Ni from the optimal path. Actually, there is one from the optimal path, which is in the open list. And for Ni, all its ancestors is N1, N2 up to Ni minus 1 are in the closed list. And therefore, G and I is equal to G star. So there is a node in the open list to which an optimal path has been found. Okay. The proof is by induction on the number of iterations J. The basis of induction is the following: if J is equal to 0, then S is in the open list and S satisfies the state. Okay. The optimal path to S has been found previously. Okay. Hypothesis. Let the statement be true for j equal to p, then Pn equal. Okay. So let Ni be the node satisfy this statement. That means Ni is in the optimal path. S is definitely in the optimal path. And all ancestors are in the closed list. The path to Ni which is in the optimal path has been found. So the optimal path to Ni which is in the optimal path has been found. Induction step. Iteration number j equal to p plus 1. This step has two cases. Case 1 is expanded and into the closed list. Then n I plus 1 from the optimal path comes to the open list. So n is child has come to the open list. Node n satisfies the statement. Okay, and if I plus 1 is in the closed list, then I plus 2 satisfies this property. Case 2 is node x, which is not equal to n, is expanded. Now, n is kept in the open list. Therefore, n satisfies the statement. This step, case 1 is involved. Okay, and this is one of the most important points about the optimality of A star algorithm. So go through the steps in the slide. Problem to ask me. Now we describe based on this property the properties of the A star algorithm, which are we will describe in Nils Day itself. Replicating the proof that it's given there. And algorithm is called admissible. It always terminates in optimal. Okay, this is the definition of admissible. Two conditions that we satisfy. It terminates in an optimal. Here, A star is admissible. Okay. And do you remember what is A star algorithm? A star algorithm is defined by V always maintaining the least cost path from S to N. And H, the estimate of the cost up to the goal node is less than or equal to H star. That is the meaning of H star. Anytime before H star terminates, there exists on open list node N such that Fn is less than or equal to H star. What is H star? H star is the cost of the optimal path from S to a goal node. So what F star S is G star S plus H star S. G star S is the cost of the optimal path from S to S, which is equal to 0. And H star S is the actual cost of the least cost path from S to the goal node. Okay. So if it is always a node in the optimal node list such that Fn is less than or equal to H star S. Okay, so here is the steps towards the proof. First observation is that for an optimal path S N1, N2 up to G, most of the proofs involving A star algorithm you can start with an optimal S goes to N2 up to G. Now by definition, H star G is equal to 0. Okay, the actual cost of reaching from goal node to goal node is equal to 0. And G star S is equal to 0. And F star S is equal to F star N1, F2, F star N3, up to F star G. So the value of F star for every node in the optimal path is equal. Okay. What you gain in G star, you lose in H star. The gain in G star is equal to loss in H star. So these export values remain the same through the optimal. Yeah. So now H star in I is equal to H star S. And I is not equal to S. And I is not also equal to G. So this equality of H star S. So let's go through this maths, okay, very carefully. You need to go back to it. Slides. So H star Ni is equal to G star Ni plus H star. H star Ni plus 1 is equal to G star Ni plus 1 plus H star I plus 1. G star I N plus 1 is equal to G star Ni plus C Ni plus 1. C is the cost of the active both Ni plus 1 is the optimal path. Now, H star in I plus 1 is equal to H star Ni minus C Ni. The above equation solves if the path A is optimal. So from this, you can see that on the optimal path from S to G, the H star value is in red. Okay, where reference H star is H star. Now we are ready to prove the admissibility of H star. First, we have to prove that H star always converges. And then we have to prove that the path of the H star is optimal. A star always calculates finding optimal path to the goal if such a path exists. There is an intuition. In the open list, there always exists a node N such that Fn is less than or equal to H star. This needs to be proved. This is the level to which the theorem is found. So this needs to be proved. One needs to be proved. If A star doesn't terminate, the H star of the nodes expanded become okay, because the G value keeps on increasing. All the arcs, the G value will keep on adding. Keep on adding arcs to the top. So 1 and 2 together is inconsistent. So if G becomes unbounded, then F value also will become infinite. But FLUC is upper bounded by H star. Hence, H star must have this is a So lemma, any time before H star terminates, there exists in the open list a node in such that F is less than or equal to H star. This is the class of the proof. So for any node on the optimal path, Fni is equal to Gni plus Hni. Since Hni is less than or equal to H star, this must be true. GNI this GNI plus HNI must be less than or equal to G star plus H star Ni. Okay. Also, H star Ni is equal to H star. Let N dash be the first total of optimal path that is a open list. Since all parents of N dash are an optimal path bound to CL, G N dash is equal to G star N dash. H N dash is less than or equal to H star. So if N dash is less than or equal to H star. And making use of the previous observation that on the open list, there is always a node, all these ancestors are equal to the closest. The optimal path of the node has been found. Okay, so this node, this LS node is special. It is on the optimal. Okay, and a path to that optimal path to that node has been found. There has to be one such node. And for that node, the heuristic value is less than or equal to H star. G value is H star, H value is less than or equal to H star. Therefore, it must be the case that the F value of N is less than equal. So if A doesn't terminate, let E be the least cost path of all in the search path. Then GL is equal to is negative than equal to E to N, where N is the number of paths in the path from S to N or so forth. If A star doesn't terminate GL and hence FN, HN is greater than equal to 0, HN is not negative, it will become unbounded. This is not consistent with the derivative. It's going to terminate. Okay. So, yes. So let me just touch upon the key points. First point is that there is a node from start to goal node in the optimal path, which is in the open. Only I don't know. If parameter new, which is that node, which is the optimal path, it will go and pick it. Okay. When we say that the algorithm is only CA, okay, it is an all CA algorithm or an algorithm which is properly planned. We are discussing artificial intelligence and not algorithms. So the importance of knowledge is supreme. When we came up with this display characteristic, will we apply any problem knowledge? We did. We applied the knowledge that this guy has to go to its destination position. We applied more knowledge. We introduced the there is no diagonal movement of it can also jump into this thing. All we can do is to take the x movement. So this x movement plus y movement is crossed. This logic also we okay. So now we say that from the optimal path, some node must be present in the open list. Otherwise, the journey to the open list to run to the whole view and the graph is clear. Second point is little more intriguing, which requires an investigation. That there is such a node on whose ancestors are in the open. So the node is in the optimal path with the optimal path with the node. Okay? So such a node will satisfy the property that its airframe is less than or equal to x plus the cost of the optimal path is stable. Now, if we keep on adding no, the airframe will become unbound and that is not necessarily the observation. Okay. Now, in the hand, please verify the inspection, which is that node, which is in the optimal path. In the optimal path. Even a question. R is R2 between classic. Okay. So this establishes the fact that we have cabinets. Now we have to prove that if we have cabinets, the path it is found has to be optimal. There is no other. Has to be optimal. Okay. The path found by A star is optimal with the star. Proof is by contradiction. Suppose the path found is not optimal. Let G be expanded in the not optimal. G is the whole. At the point of expansion of G, we know that if G is equal to GG plus HG. Now, this is equal to GG plus 0 because HG by definition is 0. Now, GG we are saying is greater than G star G because the path is not optimal. Okay. G star T is G star S plus H star S, which is equal to H star S. H star S is the constant document. Okay. These contradictions show the path should be optimal. Why is it a contradiction? It is a contradiction because how come we chose G for expansion when there was a node in the open list whose A value is less than or equal to X? Okay. So if G value, if the path to G is not open, its F value must be greater than X values. Okay. So G could not have been picked up for expansion because there was a node in the open list whose F value is less than or equal to X values. This we just prove. Okay. So the path found to the goal node will be the optimal. Okay. So this is the proof that H star is admissible. I do not expect you to, fully answer the proof in class. Just go through the slide. Go over it. So summary of advanced admissibility, it's the algorithm arms, it's the algorithm finds optimal path. Now there are interesting consequences. If Fn is less than F plus, Kt less than F plus, then node N has to be expanded before target. This is the clue to the understanding that if the heuristic value is not very good, if the heuristic is not well informed, it's not close to the actual value, then there will be lots of useless extraction because if Fn value, which is Gn plus Hn, is strictly less than F stars, it has to be expanded before target. Why so? Because for the goal of G, the Fn must be equal to F stars when it is on the open list. And if there is a node whose F value is strictly less than F stars, and since we expand always, which are the least expanded. That's a different circle expand so many useless nodes because H is here. And then consequence is if H star doesn't expand the node N before travel, then Fn must be greater than or equal to H star. If H star doesn't expand the node okay, before travelation, then Fn must be greater than or equal to F. This also follows from three. Okay. So these flags are useful. These flags are useful to prove that a more powerful heuristic is more efficient. There is a reduction of this algorithm whose H value is closer to H star will expand less number of them. That proof also we did. That's okay. Very simple. So these are the things you will have to establish. Please understand the proof carefully. H star algorithm has many nuances and they are very popular topics for questions in the evaluation. So probably all H star algorithm. Now, listen to exercises. Prove that if the distance of every node from the goal node is known, then node swap is necessary. If the H value for every node overestimates the H value, these are the things we should prioritize. If the H value for every node overestimates the H value by constant, then the path found may not be considered after the path. Now, if H value is greater than H star, the strategy is pessimistic strategy. And the pessimistic strategy is not guaranteed to give the outcome. This also should be that overestimate H star, then the path found is not necessarily optimal. Now, in that case, what is the value of estimating strategy? If you are interested in only some I'm interested in exploring this number, which can happen if H is greater than H star. That is fine. You're interested only in star, not myself. Okay. So you're interested in somehow to get to the question. You look at which path is better, which which path is better. So you have to go to some place in Bombay. That is you- okay. Now, any questions? Let's speak about it. Okay. Then let me go back to some more foundations which are critical for some foundational points. There is a hypothesis called Church-Turing hypothesis. Okay. So a person here is interesting for the following reasons. One is there are intricate mathematical discussion, which is happening to some of you who are mathematically inclined. There are challenging programming and implementation tasks, which is happening to some of you who are interested in engineering aspects. And there are deep philosophical questions, which is happening to some of you, which are who are that appeal. You are interested in understanding the meaning of existence. Okay, meaning of intelligence. So that you need to go through. The philosophical questions, engineering questions, mathematics, and many times you need physics, information theory, and so on. So please take a holistic view of the topic. Do not be narrow in your expectation from the course. Oh, I'm an engineer. Only more. I'm not interested in anything. That will not. So that will not do. I'm a philosopher. I don't care about coding. No. Okay. You need a very nice blend of all these things to do well in here. Okay. So the chart theory hypothesis is that it is a hypothesis, not true. Anything that is computable by a Turing machine. Conversely, the set of functions computed by a Turing machine is a set of all and only computable functions. Okay. What is a Turing machine? Turing machine is a very simple device like this. It has a finite state length, okay, and an infinite state, which is the memory. All these symbols are existing. The head moves from one cell to another. By reading the symbol, it can optionally write a symbol or move or do both. Okay, so this is a Turing machine which you must have done a theory of computation. Uh, the Turing, there's a model of computation given by Turing, and it captures any computation. Okay. Another application of computation is model prediction, where there is a CPU and memory. There is information transfer between CPU and memory. Now, chart theory hypothesis says that anything that is computable, uh, anything that is computable with a machine. You look at any other machine. Okay. And whatever Turing machine can compute is a set of all and only computable functions. Okay. So, so this is the chart theory hypothesis. Then there is another hypothesis called physical symbol system hypothesis. This is due to Newton and Simon. Newton and Simon. Simon is uh, Simon is one of the notable figures because he is the person who got Turing Award, the highest award of computer science, as well as Nobel Prize in economics. Okay, and he is not the only one. In recent times, we have another individual, Jeffrey Hinton, who got Turing Award and Nobel Prize in Physics and Turing Award. The physical symbol appears reads the following. Very profound. For intelligence to emerge, it is enough to manipulate symbol. You need nothing else. Okay, no mystery. Just have symbols and manipulate symbols. Okay, and what symbols? Symbols on the shape of a Turing machine. You want to create a system that understands a scene symbol, and then create a system which understands language processing symbol. It is only symbol. The next foundational part is the society of mind. Intelligence emerges from the interaction of very simple information processing unit. Whole is larger than the sum of parts. Okay, this society of mind hypothesis is due to Marvin Minsky. Read that book. Okay, it's a very profound book. Every discussion is one page long, only one page. It's a collection of thoughts by Marvin Minsky on foundations of Martin Minsky is also as a father in MIT. Then the next foundational part is the haunting problem. It is impossible to construct a universal Turing machine that given any pair M and I of Turing machine M and input I will decide if M haunts them. So this you have probably done in your theory of computation class. It's called computability. You need to diagonalization and show that it is impossible to have a universal Turing machine that can decide the haunting of an Turing machine on any given input. In general, it is not possible. This also implies that you cannot create a universal debug. What has this got to do with intelligent computation? Think about it. Okay. And let me stop here today. There are more foundational points. We'll meet again tomorrow.